Hello? Can you hear me? Okay, so shall we start? Hello. So welcome to the very first session of Eurovis 2020. The first session is about multivariate data visualization. We have very nice full talks. The first talk will be given by Michael on parallel coordinates.
Hello and welcome to this Eurovis talk. My name is Michael and I'm a PhD student in the group of Daniel Keim at the University of Constance. Today I'm happy to present you our paper about reordering strategies for parallel coordinates. Parallel coordinates are a popular and well-researched technique for high-dimensional data, which can be used to tackle a broad number of different analysis tasks. Each dimension is represented by a vertical bar, while data records are encoded as polylines spanning across the axis. One of the major challenges in parallel coordinates is how to arrange the axes. Let's look at an example dataset, in which we order the dimensions by different algorithms. It's easy to see that a different arrangement of the axes changes the visual pattern significantly. The question is now, which is the right ordering technique for a particular analysis task, and in the case of this paper, to identify clusters. If we're looking into the literature, more than 30 reordering strategies have already been developed. However, often we do not know the pattern a particular algorithm is aiming for. Often algorithms follow similar concepts. Sometimes different algorithms are proposed for the same analysis task. Most importantly, there is no empirical user study so far to make an educated selection of a reordering technique. Our paper wants to push axis reordering research forward. We make two contributions. First, we provide a classification of reordering algorithms and group them based on their intended patterns and inner workings. This helps to provide guidance in selecting an algorithm for a particular application. We also implemented a set of 14 strategies for a practical usage. Second, we conduct the first empirical user study to compare two reordering strategies for cluster identification tasks by measuring efficiency, accuracy, and the confidence of the user. As secondary contribution, we provide a new benchmark dataset for follow-up studies, which is publicly available along with the analysis results. For the first contribution, we conducted a structured literature search and identified 31 different reordering strategies. We grouped these strategies into algorithms solving an optimization problem, efficient reordering algorithms, and sorting of dimensions based on some properties. To name a few, we can see, for example, the prognostic features by Dasgupta and Kosara, or the first proposed ordering method by Ankast et al., which arranges similar dimensions next to each other. Next, we were interested in identifying the patterns that a particular algorithm is aiming for. To get an overview, we first identify interesting patterns in parallel coordinates, for example, different cluster structures, or positive and negative correlations. In total, we came up with 13 different patterns, which we added as columns in our table. Then we identified for each particular technique whether it favors a pattern, assuming that particular pattern is in the data, or whether it avoids the pattern. We also indicate if the mapping depends on the data or algorithm properties. We do this for all algorithms in the table. One can see that most algorithms are either designed to identify clusters or for correlations. We add further metadata about reordering as additional columns in the table. Please refer to the paper about these details. We want to highlight one interesting finding in the table. In the last column, we show the evaluation type which has been performed. We can easily see that all papers, except 3, have been evaluated by showing a use case or an example. 3 approaches were compared with other techniques, but without the user. So far, no empirical user study has been conducted. This is where the second contribution of our paper pops in. The second contribution of this paper is an empirical user study. We focus on cluster identification tasks. Many approaches use a similarity-based layout for cluster analysis. This means the dimensions of the parallel coordinates plot are arranged in such a way that neighboring dimensions are as similar as possible. Let's use this parallel coordinate plot to see how the similarity-based layout works. The similarity between neighboring dimensions is measured, and then the average of similarity is used as an objective function. This objective function is then maximized using heuristic or brute force approach. The result is a plot in which clusters can be traced easily across the different dimensions. However, a similarity-based layout may not be the best option in all cases. In particular, when we add noise or clutter to the data, then the visual patterns start to fade out. This effect gets worse when we add more clutter to the data. Now, if we order the dimensions by dissimilarity rather than similarity, then the clusters in the data are much more salient. Ordering by dissimilarity creates parallel coordinates with line segments that have strong slopes instead of more horizontal lines for a similarity-based layout. These diagonal lines are rendered closer to each other. This leads to less background between lines, and therefore clusters appear more dense in a dissimilarity-based layout. This effect is inherent to the parallel coordinates technique and independent of a particular rendering, as we have shown in a recent paper at this. While clusters are visually more prominent in a dissimilarity-based layout, these charts are also more difficult to read due to the zigzag-like patterns. Therefore, we formulate our research question. Is there a difference between a dissimilarity-based and similarity-based layout for cluster identification tasks? If yes, which ordering should be used and why? In our study, we measured accuracy, efficiency, and the confidence of the user as dependent variables. First, we just looked at clutter in general to have a baseline. The first hypothesis is, with an increasing amount of clutter, the cluster identification performance drops, independent of the ordering, as cluster structures are less salient in the PCP plot. Second hypothesis, without clutter, users perform better in a cluster identification task when the axes are ordered by similarity instead of dissimilarity, as clusters can be followed more easily. Third hypothesis, with clutter, users perform better in a cluster identification task when the axes are ordered by dissimilarity, as clusters are visually more prominent. In this talk, I will only present the results of the second and third hypothesis due to time constraints. For the study, we recruited 31 participants with an InfoVis background. We used both synthetic and real-world datasets. The first independent variable is the clutter level, which is defined as no clutter, 150 clutter points randomly distributed across the dataset, and 300 clutter points. The second independent variable is the ordering strategy. Here we used a similarity and dissimilarity-based layout, using the Euclidean distance as similarity measure. The study consisted of 3 tasks. In this talk, I will present only the result of one task. We showed the participant a parallel coordinates plot ordered by one of the two strategies. The participant had to mark all clusters in two neighboring x's. After confirming the selection, they rated their confidence on a 5-point Likert scale. The accuracy of the clustering is computed using a Jacquard index with respect to the ground truth clusters. This task was repeated 16 times per participant, and we gradually increased the difficulty by increasing the clutter levels. For datasets without clutter, the participants performed the selection task significantly faster using a similarity-based layout. We did not find any significant differences for the cluster accuracy and confidence. However, in the qualitative user feedback, participants said, for example, that the structure of clusters is clearer in a similarity-based layout, or that they preferred it since the lines do not intersect with each other in a majority of areas between the two dimensions. Therefore, our first design consideration for clutter-free datasets is to prefer a similarity-based layout. For datasets which contains clutter, these similarity-based layouts are faster. However, the results are not significant. In terms of accuracy, the participants performed significantly better using a dissimilarity-based layout for both clutter conditions. The users were also significantly more confident with the dissimilarity-based layout in cluttered datasets. In the qualitative user feedback, they mentioned, for example, that the spikes make the clusters more obvious or clearer because the zigzag makes it easier to see the patterns among the noise. Based on these findings, we derived a second design consideration to prefer dissimilarity-based layouts in cluttered datasets. Of course, our study has limitations. Among others, the number and population of participants and the structure of the datasets should be taken into account when interpreting the results. We have presented a classification of reordering algorithms and an empirical user study which evaluated two different reordering strategies for cluster identification tasks. Based on our findings, we propose a novel reordering method arranging dissimilar dimensions next to each other, which should be used in cluttered datasets. If you are interested in trying out different reordering algorithms for parallel coordinates, then feel free to explore our online prototype, where you can also upload your own data. Thank you very much.
Hello. So I'm ready to take some questions. First, I'll check YouTube channel. So one of the questions is about correlation magnitude for similarity. That is both correlation and anti-correlation related to similarity. So could you answer this question?
Could you please repeat the question? I didn't get it yet. Okay, now I see the question. So the question is, often one uses correlation magnitude for similarity, both correlation and anti-correlation relate to similarity. Can you discuss that? If I get that question correctly, it's kind of like asks whether in which way we can use correlation and its magnitude as a similarity function to arrange the axis.
Hello everyone, my name is Thomas.
if I relate that to the user study that we did, then we basically use a positive correlation in terms, or a positive correlation is in terms of using this rather similarity-based arrangement, whereas for negative correlations we get this zigzag-like patterns as a dissimilarity for this dissimilarity-based layout. I'm not sure whether this answer goes in the right direction. Maybe so the question is that does that answer the question, or should I go a little bit in a different direction?
Okay, the question was from Lars Linsen. So is it enough answer for your question? Similarity as correlation magnitude? Probably I take the second question. So there is another question about vertical reordering in a dimension. Have you ever considered about vertical reordering in a dimension? Vertical reordering.
A vertical reordering. And so in our study we haven't looked at that. So basically, what you mean is flipping the axis as an option, if I get that correctly. There are many papers that do this in kind of like manually, in a manually fashion. And so we haven't investigated that in the study, but what we get as what we got sometimes as a feedback that a dissimilarity-based layout is easier to detect the patterns, but is more difficult to kind of understand the patterns. So one idea for an interactive tool could be that the dimensions are ordered by dissimilarity to get this zigzag-like pattern for identifying the clusters, and then press a button and flip the every second axis to get more a similarity-based layout to then understand the clusters in a better way.
Okay, thank you. And another question is whether the result of the empirical study would be different if you use edge bundling.
That's a good question. So the main problem that we faced in the that made a dissimilarity-based layout within a clutter condition performing better is that the clusters is kind of fading in the or is fading out within the noise. So if we apply edge bundling, and this edge bundling would reduce the effect of the clutter, for example, by when we have these bands of the different of the different clusters, then it might be the case that the similarity-based layout is also for clutter condition a good option, or even a better option. We see in our results that for when we don't have any clutter in the data, then the similarity-based layout was preferred by the participants. So if the edge bundling does reduce the effect of clutter, then probably it's also a better choice for cluttered data sets.
Okay, so thank you for answering all the questions. I think there's no other questions from Discord. So I think because of time, I think we have to move to the second talk. So I'd like to thank Michael to giving the very nice talk. Thank you.
Thank you.
Thank you. Okay. So the title of the second talk is about Sunspot Plots, and Thomas will give a talk.
Hello everyone, My name is Thomas Trautner, and together with my colleagues from the University of Bergen in Norway, Fabian Bolte, Sergei Stopper, and Stefan Bruckner, we developed Sunspot Plots, a model-based structure enhancement for dense scatter plots. And first of all, let me start by telling you what inspired and motivated us, and why we thought that already established techniques are not enough. On the left, you can see a scatter plot. It can be assumed that scatter plots represent 70 to 80% of graphs used in scientific publications. They encode individual data elements as markers placed on two ordered orthogonal dimensions. They can, for example, encode local and global regression patterns, clusters, and outliers. But unfortunately, overplotting makes them less effective, and these characteristics become increasingly hard to detect. Well-established techniques such as opacity regulation, like alpha blending, the reduction of marker size, and subsampling can increase the readability, but only to some degree. On the right side, you can see a density-based visualization using a heat map. They interpret the data points as samples of a continuous phenomenon, for example by using a kernel density estimation. Even if datasets are highly overplotted, global patterns and density distributions remain visible. But unfortunately, they are not well suited to depict individual data points and local variations anymore. Our goal was a novel technique that communicates dense data as continuous data distribution, while preserving the discrete nature of data samples in sparsely populated areas, so-called sunspot plots. We therefore started our research by exploring related and inspiring work that is already out there. Splatter plots, for example, combine smooth polygonal shapes enclosing dense regions and subsampled outlier. Unfortunately, these color blending may synthesize new colors that are difficult to interpret. Similar to their approach, we consider a kernel density estimation as an elegant solution which is not limited by the number of underlying data points. A second work that inspired us was ellipsoid pixel placement in combination with shading. Related to their approach, we believe that additional illumination cues can emphasize local variation and highlight structures. A study that also influenced our design process was a spatialization design paper comparing points and landscapes. Within their setup, we consider the choice of the right camera position as especially relevant since occlusions can much easier occur in 3D than in 2D. Continuous scatter plots represent another approach that can handle an increasing data size while avoiding overplotting, but unfortunately, they do not preserve the discrete nature of the data in sparse regions. Stream maps represent an approach that is capable of smoothly blending points using an adaptive kernel density estimation, again showing that kernel density estimations are not only popular in statistics, but also in visualization. Another inspiration from a related field is the visualization of graphs as continuous fields, rendered as color-coded maps, height fields, or set of contours. In summary, these and many other related papers have inspired us, and next I finally want to introduce you to Sunspot Plots. Sunspot plots represent a visualization technique that communicates dense data as a continuous data distribution while preserving the discrete nature of data samples in sparsely populated areas. To create an expressive sunspot visualization, our technique requires 4+1 steps. The first step is rendering the dataset as a classical scatterplot with regular opacity regulation using a discrete kernel. The next optional step is a pilot kernel density estimation, which is only required if the user prefers an adaptive kernel density estimation where the kernel size is small if the region is dense and the kernel size is large if the region is sparse. The second step is the actual smooth and continuous kernel density estimation using either a fixed or an adaptive kernel size. The third step is a reconstruction of a surface model based on the estimated density from step 2. And finally, we blend the discrete as well as the continuous representation based on the estimated surface model, including the possibility to additionally apply an illumination model emphasizing surface properties. In the following, I want to describe the individual steps in detail. As already mentioned, the first step is interpreting the data as a discrete phenomenon by depicting the sample points as conventional scatterplot. We therefore consider the individual points as samples of a probability density function fh of x and a discrete kernel function k. We do this by applying a kernel function k with bandwidth h, compute the distance from the point x in space to all n sample points xi of the dataset. If a point in space is close enough to a sample, the kernel returns 1, otherwise 0. The result corresponds to an opacity-regulated scatterplot that already allows the user to distinguish between different densities until an opacity threshold is reached. In order to capture the continuous phenomenon of the data, we interpret the underlying distribution as two-dimensional fields that we can approximate through a model. Again, we consider the individual sample points as samples of a probability density function, where the probability density function at the point x can be computed through the addition of kernels at the positions of each data sample. Assuming that k again is a kernel function, h the corresponding kernel bandwidth, and n the number of samples xi, and sigma defines the width of the Gaussian kernel. The possible result is shown as color-coded image on the right, where blue corresponds to the sparse and yellow to the very dense regions. By using an on-the-fly kernel density estimation, we can even achieve an interactive performance, allowing the user to adapt individual parameters in real time. In the following step, we utilize the strength of both approaches. With the Porter-Duff overoperator, we smoothly blend the continuous surface model over the discrete data representation using an importance function alpha. The importance function alpha corresponds to the normalized continuous probability density function and can directly be used as surface opacity while blending. As shown in the image on the right, the resulting visualization emphasizes discrete samples in sparse regions and the surface reconstruction where enough samples were present. Our resulting visualization is already capable of encoding the distance to the surface. In other words, the absolute value of the probability density function by using colors. Additionally, we want to be able to encode important visual attributes like the orientation of slopes and the impression of contours, which can be seen as accessibility of the surface area. In other words, to which degree its hemisphere is obscured by neighboring surfaces. Therefore, we add the support for local illumination models like, for example, Phong or Blind Phong in combination with ambient occlusion. Next, I want to demonstrate the strength of sunspot plots based on 3 real-world datasets from different scientific fields. As first example, I want to present the 2014 Boston Marathon dataset, containing the results of approximately 32,000 participants. The x-axis of these plots encode the BIV number, which is assigned to each participant, depending on the qualification time. The faster she was, the lower the number, and the earlier the starting time. The y-axis encodes the total time in hours the participant needed to finish the complete marathon. The figure on the left shows a classical scatter plot, using opacity regulation, including an orange polynomial trendline as an overlay. The figure on the right shows the same dataset visualized using sunspot plots. In comparison to classical heat maps, in our visualization, the individual points within sparse regions are preserved, similar to scatter plots. For example, the participants of the wheelchair race within the lowest BIB numbers, with a finishing time between 1 and 2 hours. In addition, it becomes visible that sunspot plots, in comparison to classical polynomial trend lines, clearly show the trend can be well approximated with a BIB number between 0 and 27,000, but only fuzzy and less meaningful between 27 and 36,000. As second example, I want to present a dataset containing the geospatial locations of cities with more than 500 inhabitants worldwide, accounting for approximately 190,000 entries in total. In this example, sunspot plots can help to explore the agglomerations of cities and reveal environmental conditions that influence cities' development, such as mountain chains or valleys. The red circle, for example, visualized our magic lens feature, revealing the exact catchment areas and suburbs of Paris. It uncovers inhabited areas and the resulting large-scale road network in northern France. Right next to it, we can observe large clusters around Frankfurt, Zurich, and Milan. It simultaneously shows that the cluster around Frankfurt is more widely populated than the concentrated area around Zurich. And because of the Alps, the area between Switzerland and Italy is only sparsely populated. Finally, and in contrast to pure density encoding, I want to draw your attention to the individual cities that remain clearly visible, although the surrounding country is evenly but only sparsely populated, for example Lithuania or Russia. As last example, I want to present a sunspot plot of a database of handwritten digits containing 10,000 grayscale images of the labels 0 to 9. This example should again justify our design decisions. The figure on the left shows a heat map representation in comparison to a naively blended combination of both, a heat map and a scatter plot in the middle, where points are simply drawn on top of a heat map, and a classical opacity-regulated scatter plot on the right. Although this dataset is comparably small, it already becomes visible that when naively blended, it is no longer possible to perceive the density of regions that contain sample points. The figure on the right visualizes the same dataset as sunspot plot, including annotations of the implicitly created clusters of the corresponding numbers from 0 to 9. Our main concern was that blending of individual points and density representations might negatively influence the user perception. We therefore conducted a user study to analyze the human visual perception dealing with dense scatter plots, overplotting, and density estimations. In total, we compared 5 different visualization stimuli: scatter plots, colored scatter plots, continuous heat maps, sunspot plots, and shaded sunspot plots. By assigning always one visualization type to each participant, we avoided the learning bias, and in addition, the order of the tasks was randomized. In total, we had 350 participants, corresponding to 70 per visualization type, ranging from 18 to 68 years. In the beginning of the study, participants saw a set of instructions, and the practical trial including the correct answer and how it can be obtained. Participants then had to perform 2 tasks and had to pass 2 attention checks. Each task consisted of 6 questions they had to answer. In the assigned task, user had to estimate the density value of an interval between 0 and 100 in a highlighted region within a visualization. The correct value was computed by using a regular kernel density estimation, where a value of 100 would correspond to the densest point in the data and 0 to the sparsest. The error was then computed as difference between the participant's answer and the average per pixel density within the highlighted region. In the comparison task, we highlighted 3 regions, A, B, and C, and asked the user which region contains either the highest, the lowest, or if all regions have the same density. In total, we had 3 hypotheses. H1. Density-dependent color coding of individual scatterplot points increases the user's accuracy of estimating density values in comparison to scatterplots with alpha blending alone. H2. Sunspot plots do not perform worse than continuous heat maps for absolute and relative density estimations. And H3. Applying an illumination model in combination with ambient occlusion shading to sunspot plots improves the user accuracy when estimating density values. The study results clearly align with H1, and it can be seen that participants using colored scatter plots perform significantly better than participants who just use scatter plots. Our results additionally show that participants using continuous heat maps perform significantly better in both tasks than participants who just use colored scatter plots. The results further clearly align with H2, and it can be seen that participants using sunspot plots did not perform worse than participants using continuous heat maps. Unfortunately, we could not confirm hypothesis number 3. Users of sunspot plots and shaded sunspot plots did not perform significantly differently. However, as shown in the table, we saw a significant difference between users of continuous heat maps and shaded sunspot plots, showing that shaded sunspot plots provide a higher accuracy than continuous heat maps. To conclude, I want to summarize our contribution. First, we presented a novel kernel density-based visualization technique that unifies discrete and continuous representations of large bivariate data. And second, a user study with several hundred participants in which we compared 5 different visualization techniques based on 2 representative tasks during the analysis of bivariate data. Finally, I want to mention that this work was supported by the MetaVis project funded by the Research Council of Norway. Thank you very much for your attention, and if you have any questions, please feel free to ask now.
Thank you for nice presentation. I will take some questions from YouTube. What are the limitations of sunspot plots?
I think the limitations depend on what kind of data you use. So, for example, I think it would not really make sense to use scatter plots that are sampled uniformly, for example, because they don't really provide any additional information. Another limitation that I would see is, for example, if you have so many data points that you have, let's say, more data points than pixels available on screen, and you wouldn't see individual points anymore, because then the blending of the surface representation and the point representation would not provide any additional information. So I think those are the limitations.
Okay, thank you. There is another question about which roles have the background from your experience. Which roles have the background and color choices?
I think our color choice was that we kind of want to use a perceptually uniform color map just to make sure that this doesn't cause any disadvantages for the user. So I would say that this can be applied to other different perceptually uniform color maps as well, although we performed the study only with the plasma heat map. And I think it also makes sense to pick an appropriate point color to make sure that the point color does not interfere with the color map itself.
Okay, thank you. I want to check the Discord just in case.
Yeah.
Okay, Discord chat is not very active. So I have one question.
Yeah.
About your hypothesis.
Yeah.
So could you actually, can you say that your work is better than the color, what's the name? The second case?
The heat map?
Yes, the colored version of scatter plot.
Yeah. So what we try to do is we try to find out if there was the first hypothesis, if coloring the points, for example, would already gain a benefit. And like coloring the points is better than points with similar color that are just alpha blended. But if you compare colored points to a heat map, for example, you will find out that the heat map provides better results than just coloring points alone. So our next goal was then to find out if we additionally, like when blending with points, if this would cause any disadvantages. So what we wanted to see there is that there is no significant difference, because that means that the blending itself does not make it worse, if that makes sense. And then in the third hypothesis, we tried to find out if the additional elimination would gain any additional benefit, which was not the case, but this might be a study limitation. And for example, if this is applied to other use cases, for example, this geospatial data, maybe then we would have seen a significant difference. So we will see that this might be a limitation of the study and could still provide benefits for other tasks, for example.
Okay, so maybe last question about computational cost. Is it a long time to compute? No,
like it runs in real time. The paper, like we state the exact frame times, but I would say like you can adapt the parameters in real time. You get instant feedback and you can recomputate it. So this was one of our goals to make it a real-time visualization.
Okay, so thank you for answering all the questions, and congratulations on your very nice work, and thanks for your nice presentation. Thank you so much.
Thank you too.
And I want to introduce the next talk. The next talk is about V-plot. And again, the work is done by people from University of Constance, and Michael will give a talk. Thank you.
Hello, and welcome to this Eurovis talk. My name is Michael, and I'm a PhD student in the group of Daniel Keim at the University of Constance. Today, I'm happy to present you the V-plot Designer, a chart authoring tool to design custom hybrid charts for the comparative analysis of data distributions. Analyzing and exploring empirical data and its distributions, for example based on user study results, is a core task in descriptive statistics across various research disciplines. It often serves as a foundation for a more in-depth analysis. Our paper focuses on comparing such distributions, which is a multifaceted process comprising of different analysis tasks ranging from global aspects, such as identifying the type, shape, and skewness of a distribution, to local aspects. Alongside, users also want to analyze aggregated statistical properties. While simple and specialized charts have proven to be effective, they usually do not support a combination of several tasks. For example, box plots are useful to compare median values, but they do not show whether a distribution is bimodal or helps to identify the most frequent value in a distribution. Here, bar charts are better suited. Most analytical processes do not rely on one task, but rather combine a potentially large number of different tasks. Analysts are then faced with one of the two choices: either use multiple charts to communicate their analysis on different levels, or designing an expressive hybrid chart tailored to their analysis needs. Although hybrid charts have shown to be very effective, most people do not have access to them. In addition, analysts have to rely on experience and knowledge about descriptive statistics when choosing appropriate designs. In our paper, we therefore tackle the following research question. How can we make hybrid charts for the visual comparison of data distributions that simultaneously support local, aggregation-based, and global analysis tasks and are accessible to analysts? To provide a grounding for the tool, we conducted a design study by reviewing and categorizing existing tasks for descriptive statistics. We then conducted an expert survey to find out which charts is most useful for which task. In the second part, we develop a hybrid chart, which is called a V-plot. Based on the externalized guidelines from the survey, a guiding wizard can automatically tailor the V-plot through different visualization layers and to highlight particular distribution properties. In comparison to hypothesis testing, tasks for descriptive statistics are more fuzzy. Many statistical books enumerate some tasks, but they are often not formally introduced and different wordings are used for the description. Therefore, we establish a common vocabulary and introduce a classification of tasks as a first step of our design study. We group the analysis tasks into 3 different scopes, which comprise the general analysis focus. Local analysis tasks concentrate on particular data instances, for example, reading the frequency of one value or comparing frequencies across distributions. Global analysis tasks take the majority of data values into account and analyze the entire distribution. Aggregation tasks are the link between global and local tasks and focus on aggregated statistical measures of a distribution, for example, the identification of mean and the comparison of standard errors. For each analysis task, we provide a concrete example and further properties such as the analysis type, the involved distributions, and the complexity. In a second step, we summarize commonly used basic charts, particularly designed for the comparative analysis of data distributions. We group these charts into histogram, shape, and statistical property-based approaches. In the last step of our design study, we interlink the analysis tasks with the design space for the visualizations to find out which charts are good choices for a particular analysis task and vice versa. We conducted a survey with 20 InfoVis and statistic researchers. We randomized the order of the visualizations. Then the participants indicated the usefulness of every visualization technique for a given task using the Likert scale on the left, and repeated this for all analysis tasks. To report the results of the survey, we map the Likert scale values to the following colors, and then create a mirrored bar chart. In the first group, we show the histogram-based charts. The left side encodes non-usefulness using red, and the right side usefulness using 2 greenish colors. The length of the bars indicate the relative frequencies of the participants' usefulness selection. In this example, we show the combined results of all analysis tasks. Below the histograms, we show the shape-based visualizations and the statistic property-based at the very bottom. Now, I want to highlight some interesting findings. Considering all analysis tasks, there is no chart useful for all of them. We can see that on the large red bins. Interestingly, box plots and error bar variations, charts that we see very often in publications, seem to be not useful for most analysis tasks. We can also see that stacked bar charts and cumulative distributions were reported as not useful for most tasks. Generally, the usefulness of charts differ across local, aggregated, and global analysis tasks. For local tasks, the most useful visualizations are bar chart variations. While bar charts are also useful for global tasks, there seems to be a preference for shape-based visualizations, as indicated by the dark green color. Finally, for all aggregated tasks, in which the focus is identifying and comparing summary statistics, all charts which directly encode this information are considered most useful. We also made one interesting observation for the local and global task, which aim at identifying the differences between the two distributions. Group bar charts, overlapping density distributions, and overlapping broken line graphs were reported most useful. The reason is that the differences between the two distributions is directly visualized. Hybrid charts have shown to be effective for a combination of analysis tasks. By summarizing the findings in our survey, we therefore envision an ideal hybrid plot combining a histogram representation for local analysis tasks, a shape representation for the global tasks, a direct encoding of the differences, and a representation of statistical measures. Also labels for the title, axis, and so on. We contribute a chart combining all these layers into one visualization, which we call a V-plot. On our website, we provide the V-plot designer, an interactive tool to customize all aspects of the V-plot without any coding requirements to make it accessible. One can, for example, change the default layers, remove or add particular labels, adjust the ratio of the plot, or change the color and transparency levels of all visual elements such as the shape or the histogram. Furthermore, using the same data, compare the customized V-plots with the 20 basic charts which we have evaluated in our survey. In particular, for non-visualization experts, it's hard to decide how to tailor the V-plot to their needs. Based on our survey results, we can guide analysts towards an optimized V-plot for specific analysis task combinations. To do so, we start our guiding wizard. Here, the analyst can select tasks which they consider relevant or which distribution properties they want to highlight. In this example, the analyst wants to identify the frequency of one value, compare frequency across distributions, and identify the values with the largest distribution differences. Based on the selection, the V-plot is automatically adjusted by adding layers and adjusting the color of the visual elements. Similarly, tasks for aggregated and global tasks can be selected. Afterwards, the user can continue to adjust color, size, and so on using the normal GUI. Besides optimizing the V-plot, our guiding wizard also proposes a ranked list of basic charts for the selected analysis task. This ranking is based on a weighted linear combination of the Likert scale results in the survey. In terms of evaluation, we show a use case with real data in the paper. Additionally, we evaluated the V-plot and its designer in a qualitative user study with 4 domain experts. The participants agreed to our assumption that V-plots show a lot of information that you usually only get by combining several charts. But they also mentioned that understanding the V-plots for the first time requires some training. All participants liked the easy-to-use interface to adjust the visual elements. 2 participants raised some skepticism whether the V-plots with all its layers is a good choice for a single task. However, for a combination of tasks, the guiding wizard helped them to quickly tailor the V-plots to their needs. This paper makes 2 contributions. We provide guidelines based on a representative expert survey on the applicability and usefulness of the 20 most commonly used charts to 20 analysis tasks for descriptive statistics. And to make the acquired knowledge accessible and supporting the creation of custom hybrid charts, we contribute the V-plot designer, a chart authoring tool which relies on the guiding wizard to automatically propose designs and highlight distribution properties based on the selected tasks. While our guiding wizard is limited to the findings in our survey, we want to highlight that these guidelines are interchangeable and can be extended by new findings. If you're interested in the vplot designer and find it useful, feel free to explore our online prototype, where you can also upload your own data.
Okay, so thank you for a nice presentation and congratulations on your very nice work.
Thanks.
So I will take some questions from YouTube channel. So what's the advantage over the union of the density plot and scatter?
So we haven't. So the vplot does not support scattering over the different over the distribution. However, that would be, from my point of view, a very nice extension, because for the different, if you add the scatter to the plot, you would also see the actual data points and not aggregated to the different bars for continuous data. For discrete data, I mean, it's clear the bars represent just the values, but for continuous data, we apply a binning beforehand. So adding scatter would allow us to also see the actual distribution of the individual data points more clearly.
Okay, thank you. There is another question again about scatter plot to compare the. How about the scatter plots to compare distributions?
So we haven't. Of course, the scope of visualizations that we have explored is kind of limited, as we have only used, only in quotes, 20 most commonly used charts for descriptive statistics. The main advantage of analyzing or using scatterplot would be to basically see the relation between two different dimensions, so that we can also more easily see whether these dimensions are kind of correlated. So that would be the main advantage if we use scatter plots. Yeah, that we could extend also the study to that. We made all the material of our study available, so it's on the Open Science Framework, so people can basically follow up on our study, including data and so on. And for our vplot designer is not only so it supports basically the results of the user study as a grounding for the design decisions, but these rules can be easily exchanged by simply replacing a few CSV files. So if you are doing a follow-up study, then you could simply add your own new rules into the vplot designer. That's kind of like the extensibility.
Okay, thank you. I will check the Discord whether there is any questions. Okay. Okay, so this was the question from the participants. And then, yeah, I think it's great work. And also it's very good for even visualization researchers, because we use the box plot all the time. So thanks for educating us. And
thank you.
Yeah, congratulations on very nice work. Thank you.
Thanks.
Okay, so now I move to the final talk of this session. The final talk is about star coordinate, and the talk will be given by Jose. Thank you.
Star coordinates is a well-known approach suitable for cluster analysis. It has a number of nice properties, such as showing all dimensions in a single projective view, good interpretability due to using linear projections, possibility to modify the projected view by simple direct interactions, and good scalability with the number of data points. However, knowing how to start interacting with start coordinates may be a source of confusion. Datasets, as well, are becoming increasingly more complicated by including heterogeneous data types and more complicated association between variables, causing the traditional approach to be insufficient for analysis where these conditions are present. In order to alleviate these issues, we propose to extend the traditional start coordinates approach. First, hints are provided to the user to guide interaction during the analysis process. Second, mixed data, that is, numerical and categorical data types, are included in the analysis. And finally, we provide interactions for applying stratification to the data. During the course of the presentation, we'll handle each of the proposed solutions one at a time. The user is presented traditionally with all dimensional axes for interaction. This may lead to confusion as the user will most likely not know which one moves them closer to their analysis goal. We may then provide the user with guidance. Guidance is defined by Senet et al. As actively resolving a knowledge gap encountered by users during an interactive visual analytics session. That is, in simpler words, how do we reach from where we are to where we want to be? In order to provide guidance, we provide hints to the user. The hints describe the movements where a quality measure may be maximized. Each axis is divided into subparts representing possible transformation, that is, rotation and scaling of the axis. A set of 4 transformations encompasses the complete set of possible axis movements in the traditional start coordinates. The increase in the measure is embedded within the axis by using different thickness levels. Measures can be changed interactively for a more nuanced analysis. By allowing the user to select their quality measure, we allow flexibility in the analysis goal. You can observe here in the analysis of olive oils the hints given by 2 different quality measures, namely the distance consistency measure and the Dawn index. It is easy to observe that the 2 measures propose the movement of different axes. Simply, optimizing a single quality measure will remove the user altogether. However, it is the analyst that may decide when it will be necessary to overload automatic algorithmic decisions and perform a more nuanced analysis. The hints allow us to ease the difficulty in interactions by providing an initial guidance to the user. The hints currently follow still a numerical-only approach. We haven't solved the issue when presented with a different data type. So how can we tackle the inclusion of dimensions with categorical or ordinal data types? We define the axis of categorical dimensions with a block frequency representation. That is, the axis is divided into blocks, each block representing the frequency or occurrence of a category within a categorical dimension. The blocks are visible when hovering over the individual categorical dimensions as observed in the image for attribute number 2. Otherwise, lines delineating the blocks are shown, for example, as shown in the attribute 5. The midpoints of each category is used as the mapping value in the linear transformation using start coordinates. In the case of ordinal dimensions, the block order may not be swapped. We also provide highlighting of categories by clicking at a specific block. The hints may still be provided for the categorical context by encoding thickness to the line in the interface between blocks. Let's see this in action with the chronic kidney disease dataset, where red points are patients diagnosed with the illness. The current distance consistency measure value can be observed in the upper left corner. We explore the influence of several variables such as albumin levels, sugar levels, pus cells, and club levels. Probability of a category can be observed, and specific categories can be highlighted in the projection view. Multiple overlays can be generated in order to explore different categories. We select one attribute where clockwise rotation appears thick, therefore prone to generating better quality projections. The hints are recalculated at every moment. We were able to generate a local maximum with a single variable interaction, resulting in a higher DSC value. We can observe that patients with abnormal pus cell levels are not completely separated. The categories can be shifted along its dimensional axis, and we can continue maximizing our measure. A new local maximum is reached, allowing for a full separability between classes. Now that we have tackled the inclusion of heterogeneous data and guidance to the user, we are now able to tackle more complicated association between variables. One of these complex associations is the existence of a confounder. A confounder is a variable that influences both dependent and independent variables, causing a spurious association. We can observe below the initial configuration by performing an analysis of the apnea-hypopnea index in a population. The apnea-hypopnea index is a measure used to indicate the severity of sleep apnea. We color-code the samples according to the severity. Confounded variables present in the dataset may bias our analysis. In order to alleviate this issue, we may stratify our variables, that is, partitioning the samples by variables other than the target in our analysis. We can observe what happens when we perform a two-level stratification, by age and sex. Younger population of 21 to 41 years of age have a lower incidence of sleep apnea. The incidence increases with age, as we can see in the rightmost column. We may also observe that sex has an effect on the incidence of sleep apnea, being older male participants more prone to the disease. Let's see this once again in action. We explore olive oils from different regions in Italy. We can observe the distance consistency measure value of the current projection. 8 different fatty acids concentrations were measured from the oils. Counterclockwise rotation of oleic acids showed a large thickness. We transform the vector until rotational gains are lost. We continue exploring attributes that show larger thickness. We can already observe a good separation between olive oil regions, but continue interacting until a local maximum is reached. We can observe that eicosonic acid has influence only on a subset of the data. We can generate 2 strata from eicosonic acid concentration with or without the fatty acid. The strata behave as coordinated views. We can switch interactively between strata. And the measure is defined for the currently explored stratum. A maximum in the stratum could be achieved in a single step from the previous configuration, resulting in a high quality measure value. We can focus the exploration on a single stratum. Linoleic acid appears to be a decisive factor for separating oils in the selected stratum. Allowing us to reach almost perfect quality values. We evaluated the proposed hints against the rational star coordinates and interaxes, an approach where the user interacts directly with the dimensions to define each row in the projection matrix, in a variety of cluster analysis and visual classification tasks. For example, we remove the labels of 50% of the samples of a specific class. We then task the participants to select the target class alongside with all the samples that within the selection should be labeled with the same value as the target class. A statistically significant difference was found where interstar coordinates performance was greater in terms of precision and specificity than traditional star coordinates. We evaluated as well the workload and interactions from the aforementioned approaches. We found that the number of axis interactions for hinted star coordinates were typically below the interactions of star coordinates. In terms of workload, hinted star coordinates has a larger initial workload than the other approaches due to its initial complexity. However, its workload has a lower variation than other approaches, possibly due to its learning effect. Finally, we have also evaluated the hinted star coordinates against automatic approaches such as gradient descent with different starting configurations. The plus stands for gradient descent with initial configuration based on the shown approaches. We computed the relative gain in distance consistency measure for several datasets, including 4 mixed datasets. We can observe that for no dataset, a relative loss using the manual approach was obtained, and in some cases the relative gain could reach up to 25% against automatic approaches. Adding to this, the interaction may promote understanding. That is, the interpretation of the resulting projection could be better when applying a manual approach. To finalize, we presented hint-star coordinates for mixed data. In contrast to the traditional approach, our proposed method is capable of inclusion of categorical data, providing guidance to the user, and supports confounding analysis through the usage of stratification.
Thank you for the nice presentation, Jose. Thank you. So I'll take some questions from YouTube chat. Okay, so one question is there any pre-processing requirement?
Well, the hints are based basically on what measure we want to maximize. So if the measure that we want to maximize is quite expensive, then that would affect on the hint calculations. But however, we can alleviate this issue by using sampling of the points instead of using all the points. Depends on the number of points that we're doing to do the analysis. Besides that, there's no other pre-processing requirements.
Okay, thank you. Let me check Discord. Okay. So there is no question from Discord. So I have one question. So I think your system is very interactive and useful. Is the system publicly available for other people to use?
No, right now it's not publicly available. However, each of these methodology that we have defined can be easily made. The hints, it's basically denoted in the thickness on the different locations of the points. Perhaps in the future work we'll generate a publicly available code.
Okay, thank you. Just checking whether there is another questions. Okay, so there is no further questions. So thank you so much for your nice presentation and answering questions. Okay, so this is the end of the first session of the Eurovis 2020. And we had a very nice 4 talks. And then take this opportunity, I'd like to thank everyone presenters, as well as there are about 120 people watching this session. So all the participants, and then asking questions. I'd like to thank also organizers for organizing such a wonderful event. Yeah, I had a problem in the beginning, but so far, I think it's a great conference to organize. And thank you everyone for the effort. And again, congratulations for the presenters for presenting very nice work at Eurovis. And everyone, I hope that you enjoy the rest of the conference. Thank you so much. Thank you for your participation. Thank you. Bye-bye.